Hi everyone. Today let's continue with session 7.1. So today we're going to talk about the two complex conjugate root case. Alright, so do you remember the steps how to solve system of linear ODE with constant coefficients? So here we're focused on the two-dimensional, okay? So let x be x1, x2. Well, then this system is the same as the derivative of x, the vector x equals, here we have minus x1, so negative 1, and minus 4x2. And x1 minus x2. So we call this guy to be A. Okay, what is the first step? Well, the first step is to compute the characteristic equation. Okay, so we said 0 equals the determinant of A minus lambda I. What is A minus lambda I? We subtract lambda from the diagonal elements. And the other entries stay the same. Okay, so cross multiply, but we subtract. 1 minus lambda, minus 1 minus lambda, minus 1 times negative 4. Okay, what is that? Well, this guy, they're the same. So it's the same as minus 1 minus lambda squared. But do you know this is the same as lambda plus 1 squared? Because you can factor out minus 1, then minus 1 squared is 1. So lambda plus 1 squared is lambda squared plus 2 lambda plus 1. And then minus 1 times minus 4 is plus 4. So we get lambda squared plus 2 lambda plus 5. And set this equal to 0 and solve for lambda. So this is the characteristic equation. And are we able to factor it? Not really. So let's use the quadratic formula. So 2a, a is 1, minus b, so minus 2 plus a minus b squared, minus 4ac. Well, 4 minus 20 is negative 16. Square root of 16 is 4. Square root of minus 1, that is I. So we have complex roots. So we have minus 1 plus or minus 2i. So this is the eigen values. Okay, so we have two complex conjugate roots. Alright, so for lambda equals to minus 1 plus 2i. Let v be xy, and we want to solve for a minus lambda I times v equals 0. What is the augmented coefficient matrix? So a minus lambda I, well, that is minus 1 minus negative 1 plus 2i, right? And then we have 1, we have minus 4, negative 1 minus lambda. Lambda is minus 1 plus 2i. And the right hand side is zeros. Okay, what is this guy? Minus 1, minus negative 1, they cancel. And then we have minus 2i here. And we have minus 4 and 0. 1, minus 1, minus negative 1 become minus 1 plus 1, they cancel. So we have minus 2i here. Okay, so I don't want to see the I in the 1, 1 entry. So let me multiply by I, okay, for the first row. Then I have, I squared is negative 1. So I get 2 minus 4i, 0. 1, negative 2i, 0. Can you see the first row is the 2 times the second row? So we can actually swap row 1 and row 2. That gives us 1 minus 2i, 0. And actually here I'm going to combine 2 steps into 1 step because this is a long problem. So sometimes for the easy step, maybe we can combine them together, okay? Because it's a long one. Alright, so after I swap them, I can use negative 2r1 add to r2 to Q the second row. Then this is x, this is y, this is the right hand side. And then the first row tells us that x minus 2iy equals 0. Right, everybody? So that's why here we have x equals to 2iy. Then v is x is 2iy, y, so we can pick y to be 1. Then v is 2i, 1 is the eigenvector associated with the eigenvalue 1 minus 2i. So far, so good? Okay, so in chapter 6, we talk about the complex conjugate roots, the eigenvalues. So the complex numbers, they always appear as complex conjugate pairs. So if you have minus 1 plus 2i, the other eigenvalue will be minus 1 minus 2i. And furthermore, the eigenvector is also gonna be complex conjugates pair of each other. So complex conjugates. What does that mean by saying complex conjugate of that? Well, the real part stay the same, but for the imaginary part, you're gonna flip the sign. So here, it is 2i. When you flip the sign, it becomes negative 2i. And the bottom is 1. 1 is the real part. The real part stay the same. So this is actually the v, the eigenvector will get associated with the eigenvalue minus 1 minus 2i. Do you want to check whether this is true? Okay, sure, I can check with you. Let's see. So what is the augmented coefficient matrix? Minus 1 minus lambda. So minus 1 minus negative 1 become cancel, but minus negative 2i become 2i. And then we have negative 4. 1 minus minus negative 1 cancel, but minus negative 2i, it become 2i. So now you see we can multiply by I for the first row. Then I squared is negative 1. Can you see now the first row is negative 2 times the second row is constant multiple? So we can swap row 1 and row 2. And then we can use 2. So after we swap, so here I'm combining 2 steps. After we swap, we can use 2 row 1 add to row 2 to kill the second row. Okay, so what happened? This is x, this is y, this is right hand side. Then we have x plus 2iy equals 0. So x is negative 2iy. So v is then x is negative 2iy, y, when we pick y to be 1, we get v is then negative 2i and 1. See, it's the same thing here. Okay? So they are the same. But sometimes it's good to check that, because if you see this guy is the same with this guy, that's good. You didn't make any mistake. But if you see the answer are different, then maybe there is some mistake. So sometimes it's good to check that. Okay? Alright, so what is the solution then? The solution is, if we follow the solution what we had before, it should be C1, the eigenvector 2i1, e to the eigenvalue, which is minus 1 plus 2i t, plus C2, the eigenvector times e to the eigenvalue. So e to the minus 1 minus 2it. Okay, So this is the solution, but remember, just like chapter 5, if we have complex conjugate roots, we hope to have the solution in terms of real solution. So that means we can kind of expect to see sine and cosine. So how do we get sine and cosine independent solutions, which generates the general solution? Okay, so the trick is that, look at this guy. Okay, let's figure out what it is. So this guy is, okay, this guy is 2i1 e to the minus t times e to the 2it, right? But I can do 2ti. Do you remember the formula? The Euler's formula? So if we have e to the I theta, well, that's cosine theta. So e to the I theta is cosine theta plus I times sine theta. So in that case, now we can replace the theta by the 2t. So here e equals to 2i1 e to the minus t times cosine 2t plus I times sine 2t. So far, so good, everybody? Okay, now this guy is real. Okay, this is real. So but this guy is complex number. So let's multiply this guy into all of the entries. Okay, so let's see what we're gonna change. So e to the negative t, okay, let me move it in front. And then we use 2i multiply cosine 2t plus I sine 2t. And this is 1, so we get cosine 2t plus I sine 2t. Well, that is, when let's distribute it, we get 2 cosine 2t times I plus I squared is negative 1, negative 2 sine 2t. And here we have cosine 2t plus I sine 2t. Okay, so right now I want you to focus on the real parts and imaginary parts of this expression, this vector. Okay, so what is the real part? Oh, we need more space here. Okay, so the real parts, is, okay, we have e to the minus t, and then what's the real part? Maybe it's better to use a different color, right? Okay, so the real part is this guy. The real part has no I, and this guy. So we have negative 2 sine 2t. And the bottom, we have cosine 2t. Okay, so that's the real part. What is the imaginary part? So the imaginary part, you can pick the green color. So you can see the imaginary part is 2 cosine 2t and I, okay, so because that's the imaginary part, okay, so we have sine 2t of I, right? You can factor out the I. Okay, so if we just look at the coefficients of the imaginary part, then we can get rid of the I. So now you can see our first solution let's call this is the first solution. This is the second solution. So our first solution, it can be written as let's see, it can be generated by this real part and this imaginary part. Okay, so that's why, and furthermore, you will see our second solution can be also generated by this real parts and this imaginary parts. So that's why our final answer, okay, so this guy is gonna be our new linearly independent solution, which generates the solution space. So x of t is then c1 e to the negative t, and we put negative 2 sine 2t cosine 2t plus c2 e to the negative t, and we have 2 cosine 2t and sine 2t. So far, so good, everybody? Okay, you might ask, is that real? Okay, yes, we can check them together. So, so here I'm gonna show you, for the second solution. For the second solution, if we, I can show you here. So look at the second solution. What's the difference? Well, you can see the second solution and the first solution is the complex conjugates. So for the second solution, let me use yellow color so you can see the difference. So for the second solution, I'm gonna use the yellow color. Okay, and what will change? Well, here we have a minus sign. Here, we have a minus sign. Okay, so here we have a minus sign, and we have minus 2t in it, but cosine minus 2t is the same as cosine 2t, but sine minus 2t is the same as minus, so we get minus I sine 2t. So that will give us negative here and negative here. Okay, and here we have negative there. So we have negative here, and then when we distribute, minus become positive. And then here we have negative here. So if we look at the real part, what is the real part? The real part is gonna be positive. So this guy. And the imaginary part is gonna be, let me see, minus here and minus there. Oh, and don't forget here, because minus become plus, but there's an I and I here. So I and I multiply together give us an extra minus. So actually this guy is minus. So that's why when we look at the real parts, we have the same real parts. Okay? And that makes sense because complex conjugates, the real part should be the same. It's the imaginary part, we have a sign, we flip the sign. So that's why you can see the second solution is also generated by those two solutions. So that's why we get our final solution can be written in terms of linear combination of those two new real solutions. Okay, see? Cosine and sine, they are real functions, real value function. We don't see I in our solution anymore. So from now on, if you solve system of linear equations with constant coefficients, okay, please, if you have two complex conjugate roots, after you solve the eigenvector and eigenvalue and get the solution, please express them in terms of the real functions, which is sine and cosine. So after you're done, you look at one of the solution. Okay, you can look at x1 and expand it using the Euler's formula. And then you will get the real parts and the imaginary parts. Those will be the new basis for our solution space. Okay, so and are we done for this problem? No, I believe we have initial condition. Yes, we have initial condition 2 and -1. So 2 and -1. Okay, so where's my color? Okay. So x0 is 2 and -1. So let's plug in 0. So when we plug in 0, e to the 0 is 1. Sine 0 is 0. Cosine 0 is 1. Alright, and e to the 0 is 1. Cosine 0 is 1. So 2 times 1 is 2. Sine 0 is 0. Wow. What does that mean? It means 2 is 0c1 plus 2c2. Well, c2 is just 1. And then second row, -1 is c1 plus 0. So c1 is -1. Oh, so what is our final answer? So our final answer, we have C1. C1 is -1. Okay, so that's why we get negative e to the minus t, -2 sine 2t, cosine 2t. C2 is 1, so e to the t, 2 cosine 2t, and we have sine 2t. So far, so good, everybody. Yes, so this is the final solution. Alright. You might have questions. Are those solutions really linearly independent? Well, you can always check by computing the Wronskian. Okay, so, yeah, we can do that. So do you remember how to compute the Wronskian? Yeah, so questions. So if you want to ask, which color? Okay, how about this color? Okay, so questions. So are the solutions e to the minus t, -2 sine 2t, cosine 2t, and e to the -t, 2 cosine 2t, sine 2t, linearly independent? Wronskian, what's the Wronskian? Well, you write it down, right? So e to the -t, -2, okay. So negative. So let's put the e to the -t there. Otherwise, it looks like e to the -t minus that. It's actually multiply. And here we have cosine 2t, e to the minus t. And here we have 2 cosine 2t, e to the minus t. Here we have sine 2t, e to the minus t. So cross multiply. Then you get -2 sine 2t squared, e to the minus 2t. Subtract 2 cosine 2t squared, e to the minus 2t. Do you see what happened? You can factor out -2 e to the -2t, and then you get sine 2t squared plus cosine 2t squared. And that is 1. So you get -2 e to the minus 2t. And this guy is never 0. -2 is not 0. Exponential function is never 0. So we get the Wronskian. It's not 0. So yes, they are linearly independent. Okay, so in general, yeah, you don't need to show that. I'm just thinking about whether you have the questions to ask whether they are linearly independent. And we can always use the Wronskian to compute whether those two vectors are linearly independent or not. So you might ask, okay, how about our previous examples? We can also do the same thing for the previous examples. You want to check whether these solutions, they are linearly independent. So questions. So are those solutions linearly independent? Okay, then always compute the Wronskian. So the Wronskian here is the first vector is e to the 2t, e to the 2t, and then we have minus 4, e to the negative 3t, and 1, e to the negative 3t. Cross multiply, and then we have e to the 2t times e to the minus t, that's e to the minus t, minus negative becomes positive 4 e to the minus t. So we get 5 e to the minus t. You see, this guy is never 0. So that's why we get they are linearly independent. So far, so good, everybody? Okay, so let's keep going. Okay, so here we have example 4. So let's solve example 4. Please pause the video and try to work on this problem first. After you're done, let's check our answer together. This is how we learn. So let's see. Let x be x1, x2. Well, then this system is like x prime equals 0, negative 3x2, 12x1, and 0x. Okay, so this is our A. Alright, so first step computes the characteristic equation, which is A minus lambda I. That means we subtract lambda from the diagonal elements, and the other entries stay the same. Well, cross multiply, minus lambda times minus lambda is lambda squared, minus 12 times negative 3. Wow, that is lambda squared plus 36. When we solve for lambda, we get lambda equals plus or minus 6i. So this is eigenvalues. So far, so good, everybody? And let lambda be 6i. So what's V? A minus lambda I times V is 0. Okay, so what is the augmented coefficient matrix? Minus lambda, so minus 6i, 12, minus 3, and minus lambda, so minus 6i, 0. Okay, I don't want to see I in the 1, 1 entry, so let's multiply by I in the first row. I times I squared, negative 1, so 6. Minus 3i, 0. Oh, can you see the second row is the multiple of the first row? So negative 2r1 add to row 2 can get rid of the second row. Then we have x, y, this is the right hand side. 6x minus 3iy is 0. What is x? Well, that is 3iy divided by 6. That is I over 2y. So v is I over 2y, y, and we can pick y to be 1. Then v is then I over 2 and 1. This is the eigenvector. Oh, we can pick y to be 2 because I don't really want to work with fractions. You don't, right? So I and 2. Then this is the eigenvector. So remember, you can pick y to be any number, but not 0. Okay? You don't want to put 0, otherwise you get 0, 0. Okay, so then we know for the second eigenvalue, we will get the eigenvector is the complex conjugate of the other one. So complex conjugate means imaginary parts. flip the sign. Real parts stay the same. Okay, so we know x. Do we have enough space? Okay, yes. So we know x. Well, we know x is gonna be x is gonna be C1. Which is first I and 2 e to the 6it plus C2 negative I2 e to the negative 6it. But remember when you have complex eigenvalues, you're gonna express your solution in terms of real functions. How do we do that? Look at the first solution. Gonna expand it. So this guy equals equals to, let me see. So let's expand it. We have I and 2 e to the 6it. Well, that is cosine 6t plus I sine 6t. Alright, what is that? Let's move it inside. So I times cosine 6t plus I times sine 6t. And then we have 2 times cosine 6t plus I sine 6t. Alright, so that is cosine 6t I times I, negative 1. So negative sine 6t. 2 cosine 6t plus 2i. So we can put the I at the end. So 2 sine 6ti. So what is the real part? The real part is this guy and this guy. Negative sine 6t and 2 cosine 6t. That's the real part. How about the imaginary part? So the imaginary part, okay, so here I mean the imaginary parts only consists of the coefficients, okay, the beta. So this is this guy and this guy. So cosine 6t and 2 sine 6t. So far so good, everybody? Alright, and now, so those is gonna be our new basis for the solution space. So our general solution is C1 negative sine 6t 2 cosine 6t plus C2 cosine 6t 2 sine 6t. Okay, so this is our final answer. You can see compared to the last example, we don't have an exponential term here because our alpha, when we solve our eigenvalues, we don't have a real part. The alpha is 0, so you don't see the exponential function there. And the imaginary part, like 6i, we're gonna expect to see sine and cosine 6t in our solution. And do we have initial condition? Oh, yes. So our initial condition is, what is that? 1 and 1. So let's solve that. We almost forget. Okay, or I almost forget. You didn't, right? So x of 0 is 1, 1. When we plug in 0, what happened? Sine 0, 0, cosine 0, 1. Cosine 0, 1, sine 0 is 0. So, 1 is C2 and 1 is 2C1. So C1 is half. So finally, our solution is C1 is half. negative sine 6t to cosine 6t. C1 is 1. So we have cosine 6t to sine 6t. So this is our final answer for this problem. Okay, so today we talk about how to solve system of linear differential equation with constant coefficients when we have two complex conjugate roots as the eigenvalues. Okay, so next video we will talk about what happens if we have a one repeated root as the eigenvalue. Okay, see you in the next video. Bye.